So good morning, we are Pietro De Lugas and Ivan Cadimeo from SIESTA in Trieste, and we will present you a brief overview of the Quantum Espresso suite and its main features. And the code is organized in two pieces. First, I will talk to you about a first brief presentation of the project of Quantum Espresso, the suite, and very briefly of what Quantum Espresso can do, and then Ivan will pass to the other points, that is about the GPU porting, that is very relevant to the tutorial of today, of this morning, and then a brief overview of the overall performance on HPC systems of Quantum Espresso. So just to start, Quantum Espresso is an integrated suite of process codes that perform ab initio calculation of electronic structure that is based on density functional theory, plane waves, and pseudo potentials. And it's a project that has now more than 20 years, and that it started in 2002, and it was based on the work that had been going on for more than 10 years before, and it measured the effort that was done in SIESTA, mainly about the linear response codes by Stefano Baroni, Stefano De Giorgi, and Corso, and Paolo Genozzi, and many others. And the effort that was done also, that started also in SIESTA, but then spread all over the world, about the Carparinello codes, and so so this project aimed at merging these two families of code in one main code, and the main goals of the Quantum Espresso project were the innovation, because the project wanted to offer to all the users the most advanced theoretical methods that were available in electronic structure theory, and at the same time the other goal was the efficiency. So the implementation that was offered to the users of these codes were very efficient, and were able to use state-of-the-art high performance computing machines. And thanks to the use of high-performance computing machines, the code is able to simulate large and complex atomic systems, and it's used in many fields of material science, from the classical ones as device microelectronics and spectroscopy, to the new ones as electrochemistry with the batteries that now are very important, homogeneous catalysis, heterogeneous catalysis, and many other technologies that, and the study of many other materials and problems that are at the top of material science interests. The project has been very successful, and this initiative is an open initiative, and its usage is spread all over the world. If we look at the academic publications of the code, we see that they come from all over the world, and the main papers about the code receive more than 3,000 citations. More than 2,000 citations per year each year, and if we look at the downloads of the code, also they are spread all over the world, and most of the usage is in academia. We have more than 10,000 downloads per release each year, and the code is, as I was saying, the code is used mostly in academia, but not only. Also, we have usage also from people that does research in companies and industrial institutions, and on top of this, there are many other companies that are able to use the code to offer services to these industrial research institutions. And another point where the code interacts with industries is about the validation of the hardware. Many hardware vendors use Quantum Espresso to benchmark and to validate their code, like Intel, NVIDIA, AMD, and ARM. And okay, it's not in this slide, but within Max, also we are now collaborating with our industrial partners, CPERL, Atos, and E4 for keeping up to date this effort, this benchmarking. Just let's have a look at how Quantum Espresso is done. Quantum Espresso offers three layers of software. At the top layer, even if it is at the bottom, we have the applications. So we have all the programs that are able to run calculations and to compute the properties. But Quantum Espresso also offers a set of libraries that are that enable the developers and the scientists to develop their own methods and to perform them in a very efficient way since the beginning. So we have that every one of you that is interested in developing new methods, that have new ideas, can use the code, the libraries they are in to quite quickly develop their own methods. In this last year, we have had 3 releases of Quantum Espresso, one in July 2023, plus there's been another one at the end of this year, at the end of last year, in December 2023, and we have just had a dot release of the code with the bug fixes of the last release this February. So let us see. You as users are mostly interested in the application of Quantum Espresso, and as I was saying, there are many applications. The two main ones are the quantum engines, so the PWSCF code that computes the total energies, the forces, the stresses, using plane waves and zero potentials or PAWs. It can perform all these calculations using all kinds of functionals. Also, they may do more than one. And is also the code can also be compiled with EuroCC, so any functional is in principle accessible to the code. Most of the functionals, not all the functionals, but many of them. It can perform collinear and non-collinear spin-based calculation and much more other calculation. The other main quantum engine of Quantum Espresso is the Kerr-Parrinelli molecular dynamics code that, as I was saying, is one of the 2 main codes from which the effort of Quantum Espresso derived. And this code is more fit to perform ab initio molecular dynamics. On top of these 2 quantum engines, we have a plethora of other applications that perform all sorts of calculations that can be used, that are used in material science. There is the larger elastic band. There is an larger elastic band application that performs the computation of transition paths. There is the phonon code that computes vibrational frequencies, the electric response, harmonic terms, and many other more properties that are based on the derivatives of the total energy with respect to perturbations and using linear response. Another code that uses linear response is the HP code that computes using linear response the Hubbard parameters. Then there is a suite of codes that use the functional perturbation theory to compute optical spectral excitations, and many other applications that you can read here. And even we'll show you some of the performance of this code in the second part of the presentation. And just this is a list of the operations that PW, the code that you will use today, is able to calculate. As I was saying, you can do any kind of standard DFT. You can use all standard DFT functionals, many of the libc functionals that are provided by EuroCC, and you can also use non-local functionals and compute any kind of problems that is related to total energy and forces. And it's also able to compute electric fields and Berry phases. Let us see just briefly how the input of PW is done. The input of PW is very easy, as you will see this morning. It's given by a set of name lists, of Fortran name lists. In each name list, we provide some basic information. The control one just provides the basic information of what calculation to do, what is the name file of the output, where to write the output, and where to look for zero potentials. The system one instead describes the system that you are going to use. And here, the 2 main factors that are relevant for you will be those that describe the periodicity of the system and the cutoff of your plane-wave-basis set. And just to mention here, this one defines the 2 main properties of your system. So the Bravais lattice and the reciprocal lattice. So and from this one, from the cutoff, you also can derive how large is your basis set, and your primary basis set, and how dense is your mesh in the real space when you compute the charge density. The other information that you have in the file is about the atomic species that are present in the file. Here, for example, this atomic species list here, the atomic species card that provides the name of the symbol of each of the atomic species present in the system, and the pseudo-potential that we're going to use. Quantum espresso uses the pseudo-potential to describe the interaction between the valence electrons and the ion plus the core electrons. Okay, this is obviously coded in the. This is obviously a complex topic that, fortunately for the users, is totally encapsulated in the pseudo-potential. So, strictly speaking, the only thing that the users needs to know is how to fetch the pseudo-potentials. Here there is a list in this presentation of where you can download and retrieve efficient and reliable pseudo-potentials. The places where you can look at the SSP, the repository of the materials cloud, the PS library made by Real Corso, and the pseudo-dojo repository. But you can also find much more links and to other pseudo-potentials that are used in the code in this link that is provided in the Quantum Espresso website. Then the other information that you need to provide to the code is given in the input with this card that tells you how you want to sample the period zone. Quantum Espresso is a code that performs calculations for periodic systems, and so it exploits the block theorem. So all your wave functions can be written as the product of as a product of a periodic functions time to the periodic function u of r times a plane wave kr, where k is in principle any number that is confined to the first Brillouin zone, but we obviously don't want to compute it for the infinite set of numbers in the Brillouin zone, but we just compute it for a finite set of key points that are usually given by a finite mesh of a symmetric set of key points, and then we sum and approximate the integral of this sum. Then the other thing that the user needs to know is what is the output of Quantum Espresso. There is a log file in the standard output that contains all the results, the information, and the warnings. And for the format of this file, there is not strict rule, so it's cumbersome to browse by automatically. You can find then inside the prefig.save directory, you can find much more data, much more information. For example, you have a formatted XML data file with all the results that you have in the output, but in this case they are in a formatted with well schematized format, and that can be read by Python application and other stuff. Then you have also a file, charge density file, that is used by PW to start the calculations, or by other codes to start calculations on top of the previous calculations. And also the wave functions are written in the same way with the files that are either Fortran binary files or HDF files. This is an example of how you can use the binary output of Quantum Espresso. For example, if you want to compute the bands, you first do an SCF calculation that prints out the results of your calculation, and then you use the charge density that is being printed by the first SCF calculation to compute the bands of your system. And then you use the output of this non-SCF calculation by processing utility of Quantum Espresso, band.x, that performs the symmetry analysis and saves the data for the plot. So this is a simple workflow, but it's important for the user to know where the data that are used from each part of the workflow are are saved, and this place is always the prefix.save directory. Prefix is the name of the directory that is set inside the control name list of the link. Just a few words. Another thing that the user needs to know to start the calculation, about this you will have to listen in the morning, is about the parallelism. We have many degrees of parallelization. The most simple of them work for throughput, so they just perform independent blocks of the calculation all together, and then they sum the results all together. These are, for example, the images that you will see tomorrow for performance, the pools that you will see instead today, and then there are several kinds of distribution of the work for the parts. The basic parallelization of the code instead is targeted to the latency, so to speed up the operations of the wave functions, and is based and needs high communication, so it cannot be spread to a very large set of nodes. And this also performs a data distribution. And together with this, when you use GPU, yes, you also leverage the GPUs to perform and parallelize this work inside a single API process. As I was saying, the other thing that one has to know, if one uses parallelization, one has to be aware that we are also distributing the data of the wave functions. So when you are in G-space, the data are distributed in sticks that are oriented in the Z directions. And instead, when you move to real space, because the code makes back and forth, that instead of written in real space, you have the data distributed as slices in the Z plane, as planes in the Z direction, parallel to the Z direction, or slices of these planes in the Y directions. And to go back and forth from one representation to the other, the code performs subsequent Fourier transforms from one representation to the other. So, okay, this is probably all that one needs to know to start using the code, but obviously you will need much more information about if you are interested about the code, and you can find that in a set of, for example, in the website of Quantum Espresso, where you will find all the cheat sheets about the usage of the codes with all the input variables that can be provided. If you are interested in the theory underlying the functioning of the code, we have Quantum Espresso as part. Quantum Espresso group has published in the years few papers that where these points are explained. The first one was in 2009, and the second one with an update was given in 2017, and a new one was also provided in 2020 about the GPU porting. A very recent one is the one by Ivan and all of us that was printed last year, that provides a much more detailed analysis of the parallelization, on how the code works in the parallelization, what are the useful ways of the more efficient ways to parallelize the code. And then if you want more information about the community, there is the site of the foundation.quantumespresso.org. And if you want to participate in the development of the code and submit issues, there is the GitLab. And thanks for your attention. And then now I give the floor to Ivan for the more technical part. Thanks.
So good morning, I am Ivan Carnimea, and I will continue this introduction of Quantum Espresso. So Pietro explained us, introduced the Quantum Espresso as a whole project and the main features for CPU and on the different subprograms that are present in the suite. And now I will focus more on the porting of and also usage of Quantum Espresso on accelerated heterogeneous architectures. So in the first part, I will first briefly describe the main concepts behind the porting and the usage of Quantum Espresso on GPUs architectures, and then I will conclude showing an overall list of examples and performance in order to give you an idea of what you can do and what type of system you can treat by using Quantum Espresso on heterogeneous systems. So GPU acceleration is something that is very important for us and for the Quantum Espresso project. The main motivation is also was also mentioned by previously by Daniele. So the GPUs nowadays are present in basically all the HPC systems all around the world. The most powerful systems in the world are accelerated with GPUs. And also in Europe, we have three pre-exascale machines, Leonardo, Lumi, and Mare Nostrum, that are accelerated with GPUs. And also, very recently, also Jupiter has been launched, that probably should be added to this slide. That is the first fully exascale European machine that is also accelerated with GPUs. So learning how to use GPU is something very crucial for launching calculations and for simulated complex system with realistic accuracy. We started working on GPU since a couple of years ago. The first version was of Quantum Espresso accelerated on GPU was fully based on CUDA Fortran. And at the very beginning, there were two different repositories, one with the standard version of Quantum Espresso and the other one with the CUDA Fortran version of Quantum Espresso that was intended to work for NVIDIA hardware. Then we decided to slightly change the offloading model. So we moved from CUDA Fortran to OpenACC, or better, to a mixture of CUDA Fortran and OpenACC. That is the way Quantum Espresso works now. The two repositories were merged. So from version 7.0 of Quantum Espresso, we have one unique version of Quantum Espresso based on OpenACC. So when you go to the Quantum Espresso website and download the releases, or when you go to GitLab and you see the code, you will see in the official releases and the official version the two different ways. So one for CPU and one for NVIDIA GPUs based on OpenACC and CUDA Fortran. So one version for two different models. More recently, we started also to develop another offloaded version of Quantum Espresso based on OpenMP5. And this is because there are other types of HPC machines that are based on other types of GPUs, mostly Intel and AMD. So, for example, Lumi is based on AMD, or Frontier is based on AMD. So, for those types of machines, we found that it was more efficient to use OpenMP5. So now we have, again, two different versions. So, and in this moment, the two versions are contained in two different branches. So the main developed branch is the official one that is based on OpenACC, CUDA Fortran, and works also for CPU. And then we have another branch where we are starting to implement OpenMP5 offload for AMD and Intel software stack. And in future, of course, we hope to merge all the different versions into one for maintainability purposes and also for simplicity for users. So the idea is to have one unique source code that can be deployed on different hardware. Just in order to give you an idea of the work that we do when developing the code, you can see here very briefly, I summarized the main features of the different offloading models that we use. So CUDA Fortran at the beginning was based relies on duplication of variables. So you have one variable that is for device and another for host. And when we moved to OpenACC, we could exploit directives. So to say it in a simple way, you have one variable that can be managed for CPU and GPU. So you don't have to duplicate code. And this is quite comfortable for us that we don't have to, because it reduces the maintainability burden. And now we have OpenMP5 that works in a conceptually similar way as OpenACC. So we have similar directives that manage different types of offload. So the final shape of the program of the suite, the current state of the suite, is that we have these two different models. So we have an upper level of code where basically you don't see so much GPU code, lines of code. And then we have, when you go more deep into the numerical libraries, you can see that the OpenACC directives manages the CUDA numerical backends. So from OpenACC basically triggers QSolver, QBLAS, QFFTs for executing fast Fourier transforms, eigensolver, linear algebra on NVIDIA GPUs. And then, quite separate, we have OpenMP directives that are linked with AMD and Intel software stack. So Intel OpenMP directives in this moment trigger ROCm 1MKL for linear algebra executed on AMD and Intel. In principle, these two things could be crossed, but for the moment we avoided to increase to keep the code simple. So the things now are quite separate: OpenACC for NVIDIA and NVIDIA numerical backends, and OpenMP for Intel and AMD. Let me just now go a bit more to details. Of course, you will have more specific information about how to run calculations on GPU in the following tutorials. So now Oscar and Aurora will give you a tutorial about PW, and tomorrow there will be other more specialized exercises for phonon and linear response and time-dependent linear response. Now I will just introduce the main problems or the main features when working with GPUs and when launching calculations on GPUs. So I think there are two important concepts when approaching to this the GPU offload. The first one is that, as we all know, GPUs go faster than CPU. Why? Because CPU internally, one CPU chip has a few cores that are very powerful. So one CPU core is very powerful, can execute a lot of different operations, can also manage an operating system. So, but they are few. Instead, in GPU, the approach is quite different. There are a lot of cores. You can find thousands of computing cores inside one GPU. These cores are simpler, but since they are a lot, you can, since there are a lot of cores inside one GPU, there is some kind of internal massive parallelism that is embedded inside the microchip, as Pietro was saying you before in the previous slide. So this is the reason why you go faster with GPUs. In some sense, you are moving some parallelism inside the microchip. Another important thing is that up to the current state of technology, CPU and GPUs has different memories, which means that when you write the code, you have to think about what you are doing, because if you want that GPU takes care of some portion of your code, you have to take the data, move to GPUs, execute the calculation, and then return the data back to GPU. Which means that if you don't do things properly, you will get stuck in communication bottlenecks, because you have to synchronize data for them back between CPU and GPU. So the main coding work is to do things in such a way that the code is optimized. And I think from the user perspective, this means that when you launch calculations on GPUs, you have to keep in mind that you have to check also the GPU memory, because if the calculation is large, you can go out of memory, not only on the CPU side, but also on the GPU side. Another important thing is parallelism. Pietro was introducing the different levels of parallelism that are implemented in Quantum Espresso. There are images, pools, plane waves. So how the GPU acceleration is inserted in this framework. GPU is at each rank level, which means that at the beginning of the calculation, the data are distributed among different ranks, and then each rank, when finds the particular loop that is accelerated, it offloads that portion of code to one GPU. In principle, you could also do things like using more ranks than the number of GPUs, which means that each GPU receives the workload from more than one rank. But in practice, this is a bit discouraged. The usual way we work and the usual way we suggest to use GPUs is one rank, one GPU, which means that when you are about to launch a calculation on a machine, you count the number of GPUs that you have, and then you just set the number of ranks of MPI processors equal to the number of GPUs, which means that each rank at that point will offload its workload to one GPU. And this is the way we usually work with GPU, and also that, to our experience, leads to the best performance. This is a bit more technical, but I think it's very important that it is worth to be mentioned. The most important numerical bottleneck in quantum espresso calculation is fast Fourier transforms, and in order to improve, and the algorithms for fast Fourier transforms are quite different between CPU and GPU. So one way to exploit the GPU power, computational power, is to include a synchronicity in the execution of fast Fourier transforms, which means that at a very low numerical level, FFTs are done in, the data are divided in batches, and each batch works in a synchronous way with the other batches. So each batch finishes its workload, it goes on without waiting for the others to be completed. These asynchronous FFT algorithms were introduced since the first version of Quantum Espresso in CUDA for NVIDIA, and now they have been recently extended to AMD by Fabrizio Ferrari Ruffino and Laura Bellentani using a HIP coding language. So now we have asynchronous FFTs that are also working on AMD architectures and lead to very good performance. We are also working to extend this asynchronicity to Intel GPUs. We are still working on it because the programming model is slightly different. We're working with Intel, so there is a bit more work to do. Here, just to give you an idea of what I'm saying, so the blue bar, this is a system, a chromium iodide system. This is a benchmark test case. So the blue bars here are the computational times if you run a calculation without using asynchronicity in fast Fourier transforms. Whereas the red and yellow bars is the same calculation when you use asynchronous fast Fourier transforms. I will not go through the details in the differences between red and yellow because it's still another problem. The difference there, for those who already know the topic, is GPU-aware MPI. So basically the yellow bars the calculations in the yellow bars do less communications with respect to the calculation in the red bars. So this is just to give you an idea of what you can get when you use the proper algorithms to exploit GPU power. Details of GPU porting of Quantum Espresso have been published last year in this article. If you want, you can have a look. We described basically that here there are involved all the people who contributed to the porting in the last years, and we described in quite a detail all performance and offload and porting models that we have used to offload the code to GPUs. So let me now finish in these last 5 minutes, I think, that I have, showing you some molecules. Let's go back to the materials and molecules, and just to show you some of the performance that you can get when you launch calculations with GPU. Of course, in the tutorials in the next today and tomorrow, you will be given explanations on how to optimally exploit GPUs for calculations. But of course, you will be restricted to small molecular systems for, of course, practical reasons. So here I will try to give you, to show you the results of large calculations, to show you how the know-how that you will be given in the next days can be used for real calculations. So here we have quite a large system. Is chromium iodide, is 7,000 electrons, and the gray bars are computational times for one SCF step using PWSCF on different hardware. You can see the leftmost bar is the time using for a CPU execution using 1,400 cores. And in the right bars, you can see this time is much lower by using different GPU accelerated architectures. In the last bar, you can see that using only 96 GPU, you can get basically you can go one order of magnitude faster than a full CPU calculation. Here, let me just say that comparing times between CPU and GPU execution is something that is a bit under debate, because it's not there is not a straightforward way to compare times, because there are completely different chips. The way we do this performance is a node-by-node comparison. So we think about as if we were the users, and we think that, okay, users, what do they do when they launch calculation? They fix a number of nodes, and then they decide to exploit that fixed number of nodes. So those nodes can be exploited using a CPU or using GPUs. So the comparison in times that we give are node-by-node comparison, thinking about what users could do. Of course, there are other ways to do this. This is just to give an idea. It's not a rigorous comparison, but I think it's useful to have an idea of what you can do with GPUs. Here, another example is the calculation of titanium dioxide band structure using hybrid functional, that you know that they are quite challenging with plane waves. And in the times in the plot, you can see the red times is using CPU, and the blue bars is using GPUs. Here the scale is logarithmic, so when you compare the last red bar with the last blue bar, it's one order of magnitude faster. It's not because the look at the scale is a logarithm. Another example here, we also have accelerated Carparinello. So here there is a test system done by Riccardo Bertossa in his PhD thesis, another developer of Quantum Espresso. And each point of that phase diagram is one or probably even more Carparinello simulation. So here is something that this calculation took about, I think, 100,000 separate runs to produce that plot. And here you can see the times for each Carparinello step, Verlet step. You can see that the dark bars are CPU executions, the light bars are GPU execution. You can see that using GPUs, you can treat a larger system, you go faster, which means when you use Carparinello, that you can run longer molecular dynamics, and you can produce these nice results. Another crucial code of the Quantum Espresso suite is phonon, as Pietro was that introduced before. So here another example is the calculation of phonon dispersions along the asymmetry directions for a silicon 100 surface. So here we have 500 electrons. The system is smaller because, of course, linear response calculations are heavier than SCF. In the plot, you can see, as usual, in dark red, the CPU time. In light red is GPU time. Here you can see a factor of 5-6. The gray line is the speed up. So working with GPUs, you can go 5 to 6 times faster than using the same number of nodes with CPUs. The same system here, we also computed the yields spectrum that you will see, I think, tomorrow. Again, here you can see the same comparison, and also for yields, you can see on average a factor of 5 to 6 times faster when you run on GPUs rather than running on CPUs. Of course, let me tell you it again, when you work with GPUs, you have to take care about the memory usage, because you have also to consider the GPU memory. So sometimes if you see that you go out of memory, and you might wonder why, because there is a lot of memory, there's a lot of RAM in the nodes you are using, just think that another reason can be that the GPUs might go out of memory. In that case, you should increase the number of nodes to provide more memory on GPU sides. Here there is a very more recent development that has been done in Quantum Espresso by Pietro, Oscar, Tommaso. That is the calculation of magnetic perturbation using linear response theories. So for the magnon dispersions here, these calculations are also very heavy. And in fact, the test system here is 54 electrons. This is because, yeah, the computations here are really complex and demanding. You can see again that using in the plot, you can see that using GPUs, you can do them in much more. You can go faster and you can do that more with higher performance. So I hope that we have given you overall idea, general idea of what Quantum Espresso can do and the type of performance that you can get when running calculations on GPUs. Let me just finish by mentioning all the people involved in the project. There is quite a large Quantum Espresso developers group in Trieste and Udine. In Udine there is Paolo Giannozzi, and all other people, Stefano, Aurora, Riccardo, Oscar, Fabrizio, me and Pietro, work in Trieste between SIESTA and CNR. We have a very strong collaboration with Cineca. They help us in the code development, code optimization, and GPU porting. And also we get help by the Quantum Espresso Foundation that manages the administrative and organizative things related to the management of the Quantum Espresso project. And also we have very valuable support by external collaborators and also by vendors from different companies, providers of GPU architectures, and they help us to optimize the code, maybe specifically for their own architecture and for some particular software stack. And with this, I have finished, and thank you all for the attention.
Good morning to everybody. Today, I and Aurora here present the first end section of this workshop. I will present how to run Quantum Espresso on a HPC system. In particular, today we work on Leonardo. So the recap of what we will do in this section is how to run, in particular, PW that Ivan and Pietro presented before. Now, the first three exercises are about how to run and parallelize quantum PW on a CPU, and the last exercise on GPU, yeah, because Leonardo is a GPU accelerated, so is the most important part for this, the last, but the most important for this section. Okay, PW is organized as a modular organization that allow a greater flexibility and easy to use more than the one specific algorithm, and easy to optimize for your computer, for your laptop, or for the cluster like Leonardo today. For how to work PW, you have to write an input with a molecular information that Pietro showed you before, with all what do you want to compute, and the molecular and the system information. Now, the PW solved the constant solver, and in PW is already implemented more more than one solver that you can choose. And in the end, when you solve the system, the SCF calculation, you obtain the output with the chemical and physics properties. First of all, to start the exercise, now we have to connect to the our cluster. For this workshop, we have a project on Leonardo in Cineca, Bologna. So now, first of all, we have to connect to Leonardo. So go to your virtual machine, your terminal in your laptop, and digit this command SSH your user that you have on email, or I don't know how when Cineca send you, at login.leonardo.cineca.it. So now I will move on my terminal. Do you see the terminal? Yeah.
Yeah.
Okay. Now I am connected to Leonardo. So in the first page, you can see this table with the information about the cluster. The project that we have in this workshop is relative to the booster partition. So you can see here the architecture of the booster nodes. So Leonardo has 3,456 nodes. Each node has 32 cores, 32 GPU, and each node has 4 GPUs Ampere, NVIDIA Ampere A100 GPUs. This is the memory on the GPUs, and this is the RAM on the CPU. So you can see, I read before a question about the GPU and GPU memory. So you can see this is the GPU and this is the GPU. So the GPU's memory, usually the available memory on GPUs is smaller than the CPU. So now we have to download the material for this workshop. The material is in a GitHub repository that you can see here. Maybe no, no, I have already opened before. So you can see this is the GitHub page for this hands-on. You can copy this URL and clone this repository on your partition on Leonardo. It's good practice run Quantum Espresso in a Scratch partition, because usually in our hands-on section is not the case, but usually when you have a bigger system, Quantum Espresso generate some temporary file that is very big. So you need you need a larger memory. So the Scratch usually has an area with a bigger memory. So clone the repository with command git clone. Maybe I can increase. Okay, clone and copy the URL that you can copy from the GitHub repository. Now, okay. if you check, you have downloaded this directory with all material. Yeah, now you can see the material for this workshop. Now we go to the day one directory that contains all material for this section. So cd day one, and you can see here all the materials for this hands-on. Here you can see also the slides that I show you now. Okay. Now, before starting with the first exercise, some useful links for Quantum Espresso. There you can see the website, the download page, and all documentation for the Quantum Espresso. You can see also the forum, in particular the mailing list. If you need help or have a question about Quantum Espresso, you can send an email to the mailing list and someone usually answers some question. Okay, so go for the exercise 0. So the first run with PW. This is the input for the Quantum Espresso, for the PW. Pietro already explained how to organize the input, but you can repeat. The input for the PW is organized with the block. Each block is specific for something. Now the control is specific for the general information for the calculation. Now in this example, we compute an oxygen atom. So here in the control you can see the calculation is the SCF. And also we compute the stress. So if you need more information about the keyword, about the block, about all stuff in the input, you can see this link has all information about the input for PW. There are also other links for phonon and the linear response, Caparinello. This is for the PW. So if you need some information about n-type, you can see in input in this link. You can find all information on this. So now go to the how to run a job on Leonardo. Now, first start with the GPU calculation before start with the CPU calculation. So Leonardo has the GPU accelerator, so you can't find a module with the Quantum a CPU version of Quantum Espresso. So we will use a version that are compiled by Laura Delentani from Cineca. And you can find the executable in this directory, and you are available to use it for this workshop. So this is the work area for our project today. So is a 7.2 version of Quantum Espresso for the GPU. But if you need to submit a job in a cluster, usually the HPC cluster has a queue organizer for submit the job. You can't send the job and hope to run immediately in interactive mode. You have to send a script with for the queue organizer. In Leonardo using the Slurm using the Slurm gesture. Now here I show you the the more common command to use it to use in Slurm. How to submit a job. This is the command as batch and the name of the script. To check the status of the job is SQ-U, your username, and to cancel the job if you have wrong something, you can use as cancel and the job ID. Your job ID, you can see this number when you use it SQ-U, this. So now I go to the terminal and show you how to run the exercise 0. So enter to the, maybe I can increase the dimension. Okay. Okay. Yeah. Okay. Go to the exercise 0 directory. In the directory, you can see there is a README file in each directory with the typical to run the exercise. So you need some help, you can read the README file, and also a reference directory with the result and the script that you have obtained if you have the success to run the exercise. So if you check the script that I prepared in the exercise x0 run.slurm, this is a typical script to run on Leonardo. This batch block is relative to the Slurm. So the job name is the name of the job that you can see in the when you use it the SQ command. You can change, you can write everything here. Maybe I can put my user. This is the job. This is the how many nodes do you want to use it. This example is a serial run, so we use one node. Today we always use one node because we have not much time, so the example is small. So the all examples are small. So this is the partition of, this is the limit of time, this 30 seconds, but for an atom is enough. This is the partition, this is the Leonardo partition booster that I showed you before. This cost is a quality of service, this is a specific queue. Now, all today we will use a debug quality of service because okay the system are small. Now in the serial case, how many tasks we use per node? We use one task because it's serial, so put one here. How many CPU per task? All again one. This is a serial calculation. Now, okay, this output and error is output and error file for the Slurm script, not for the Quantum Espresso. The output of Quantum Espresso is another file. Okay, and this is the account of our project. Okay, this line source and this file environment CPU is to run the CPU version of Quantum Espresso that I said before. This is a local version, a local compiled Quantum Espresso version. So we have defined some variables. In the GPU version, you don't need to source this file, but you have this file in the GitHub repository. So you haven't changed these two lines. This is how use this CPU version. These three lines define some directory that's useful for us. And now go to run the PW in serial. So this flag OMP num threads is for the OpenMP number of threads. Now, again, we now run a serial calculation, so put 1 also here. Now, how to run a simple job with PW? Now, we use always today the MPI run in Leonardo. This minus NP is the number of MPI. So again, 1. And now we have to insert the executable of PW. Now, before the path. So that is this one. So with $, and you can copy this path, in particular slash. The executable is named pw.x. Now, minus in is the input file. Now you have to put the input file. The input file, all input file are in this directory. So again, in the slash and the name of the input. Now I have here atoms minus PPE dot in. Measure and the name of the output for this the Quantum Espresso output. So I call atom PPE dot out, but you can choose any name that you want. So now we are ready to run a serial calculation of Quantum Espresso. So now the command to submit a script. So batch x0 minus run. So now now it submit, and this is the job ID. Now maybe I am fast. Yeah, you can see here I send this calculation. This is the job ID. This is a partition. My user. No, this is the name of I use in the script. My user, the timing, and the node. But I think it's finished. Yeah, it's done. And show. This is the file that's created, from PW. The XML that Ivan showed you before. This is the directory with all information that from PW, and this is the output. Now, in the output, in the first part of the output, there are some information about Quantum Espresso, the version of the Quantum Espresso, some articles to cite. There is no the last one because yeah, this version is 7.2, not the last one, and also all parallelization information. Yeah.
Yeah, can you please go back a little from the X bar when you run the file? Can you please go back a little bit? You're too fast.
Yeah, but then I give you some minutes to run the exercise and help you if you need help. Okay, I finish this output and then you have 10 minutes to run the exercise. Okay, and maybe I can help you.
Okay.
Okay. I show only some information about the output. You can see here the parallelization information. Now, this is the serial calculation. So this is the MPI plus OpenMP cores. This is one. The number of MPI, the number of threads per MPI, the OpenMP threads per MPI, one. And this is the number of nodes, one. And so you can see the available memory for this calculation. Show you before these nodes of Leonardo, depends of the machine. So in the end, or in the last part of the output, you can see if you check the exclamation point, you can see the total energy of the calculation, the number of bands here, the bands, and also the stress, because before I set to calculate the stress. And you can see also the number of iterations to converge the SCF calculation. And in the end, that we will check in the next exercise is the table of the time. We will concentrate on the total time in this morning, not in particular part of the code, but you can see in the end the table of time. Okay. Go to the exercise 1. So the parallelization with pools that Pietro presented before, how Quantum Espresso is parallelized, and I think the powerful method is using the pools. So the PW solve the typical Kohn-Sham equation. You can see the wave function, the system, and the unstabilized charge density, but we focus on the wave function now and focus on the dimension of the wave function. So you can see here, this is the wave function as 3 dimensions, the k-point dimension, the number of bands, and the number of plane waves. So instantly you can see that the plane wave is bigger, is very bigger than k-points and the bands. So if you distribute the memory, depends on the k-points band or plane waves, you can obtain this memory distribution. But usually the operators applies to a single orbital. So most of the communication are usually done along a plane wave direction. So, for example, you will do an MP sum is done along this direction and not in the other two direction. What does it mean, this? Does it mean if you distribute the memory, for example, here for the 4 ranks along the plane waves, each ranks has all k points and all bands and a part of the plane waves. So if you need to do an MPI sum, an example, this rank have to communicate with this, this, and this. Each ranks have to communicate with each other. And this is not convenient. Now, we introduce the pool. The pool distributes the number of k points for the different ranks. So now you can see 4 ranks and 2 pools. This pools and this the other. So now if you do the MPI sum, now for this orbitals, this rank have to communicate only with this and not the others. You can understand that this is very powerful to reduce the communication around the ranks. Now, for this example, we use this system, the oxide, the cupric oxide, and you can see in the input, in the last row, the number of k points that we used. So this is using a grid of 2 times 2 times 2, so in 8 k points in total. So you can use until 8 pools to distribute the memory around the rings. So now go to the script for the exercise 1. So move to the directory x1 pools. So you can see also the README file and the reference, and go to the x1 pools script. Okay, the first part is the same for the respect with the exercise 0, but now we don't run a serial calculation, but we can use yeah, Laura.
We have a workaround, so please source, I wrote it in the chat, the script that is written in the chat. Sorry, the chat of Zoom is terrible, I hate it. Vabbè, I'll put it again in the chat. And maybe Oscar, you can add it also and repeat it. So please source this file that will load all the module file that you don't see now. And
this one. Source.
Yes, so the dot, if you want to source it, or source the file without the name of the profile.sh. Yes.
Okay.
Then you should see all the modules and you should be able to do the exercises.
Okay, thanks. And we opened it. That works. Okay, go to the script now. But I have to add also in the script, Laura, or not?
I think it's fine without changing the script.
Okay, perfect. Okay, this is the same that you can see before, that you can saw before. Now, here I put all the nodes. Yeah, the calculation is fast, I think, during 5 minutes, so maybe I cannot run, so I can leave all nodes for you. This is the number of tasks. This is the number of MPI ranks that we use. The booster nodes has 32 CPU, so we can use all them. And also 1 CPU per task. This is for the OpenMP that we show in the exercise 3. Okay, this is the same, and also this. Now, I prepare here a loop to compute more than one calculation with one script. The IP variable define the number of pools. Okay, you can see here, this is the same that show you before, MPI run minus number of MPI, now 32. This is the Espresso directory and executable, the PW executable. Now you can see here 2 flags specific for Quantum Espresso. This is N pool, the number of pool, and this is the NDAG that I show you in the exercise 2. This menu is for the input, and this is the output. We prepare here a loop to possible to send more calculation with one script. So if I put 1, we use only 1 pool, the same that we showed before. Maybe move to 2 pools, 4 pools, and so on. You can try more than 1 variables. So the maximum limit here in this system is 8, because we have 8 K points. Okay. Then write and quit. And then when you change the script, so this is the script, we can modify how do you want. Now here all the value 1, 2, 4, and 8, and then you can submit the script, the same command as batch x1 and the name of the script. In the end, you have the check the whole time in the end of the output. The script generate more than 1 output, and you check the whole time and the end of each output file. So we have to check the whole time and not the CPU time, because the whole time contains because the CPU time neglects some execution time like I/O, but the whole time is the real time, the real total time of the calculation. And then when you have the check, we have check all the whole time for the different pool value, you will be able to produce a plot like this with the times in function of the number of pools. And you can see here how to scale the time respect with the pools. Now, you have, I think, 15 minutes to run this exercise. I'm here. I hope to answer in the chat or in the HMD page. And also there is Aurora, Fabrizio, Laura that can answer you if you need some help with the exercise. So I start with the exercise 2. So before I said the other flags that you can see for the PW, so the NDAG. So now the exercise for the parallel diagonalization. So this is the schema that I showed before, and now we focus on the diagonalization. Okay, the parallel diagonalization. Now here an example, the scalability for the trend for the parallel diagonalization. In this graph you can see the timing function of the matrix size, and this tree line is about free diagonalization. The MKL with one core, the same that we used for the exercise 1, and this is the parallel diagonalization with the ELBA with 4 and 9 cores. In this panel is the zoom for the for the first part of the graph. So now you can see that the parallel diagonalization is advantageous when you have a very big system. When you have a small system, the advantages is not clear. And also in our case today, we have a small example for this time. So I can show you how to run with the parallel diagonalization, but you can see the real advantages to use it. So if you check this line, is the same that we used for the exercise 1, but you can see the NDAG flags with now the ID value here. So move to the terminal, go to the directory exercise 2 for the diagonalization. Also here you can see the README file and the reference, so you can check everything. So now edit the script for the exercise 2. Yeah, the first part is totally the same. Also here we use all the nodes with only MPI ranks. So OpenMP threads put 1. And now the same loop. Now I put here only the 4, but you can try with 1, 4, okay? ID, and this defines the number of NDAG, the number of the blocks that you parallelize the diagonalization. Now I put here the 4 for n pool because you can see 4 and 8 is almost the same in this example. Okay, then you can write in Q and submit this script. So yeah, if you put 4 in an NDAG, you have the distribute memory in a block 2 times 2. No, the array, the matrix will be distributed in a block 2 times 2. And then also you can put the value for this. In this case, I run only for the four pools with NYAG 4. This is the previous results with the NYAG case. Okay, that I show you before. The parallel diagonalization is advantageous when you have a large system. In this case, you can see the advantages, but if I want you how to know you can run with the parallel diagonalization. Okay, so run and test it and ask me if you have some problem. Go with the exercise 3. Now they introduce the OpenMP parallelization. So you can understand the quantum espresso as as more than one flags to parallelize the code. So you have to understand which is the combination, the best communication for your system. This is not automatic. Okay, now talk about the OpenMP parallelization. For now, we used only one OpenMP, and now we modifying this value. Now, which are here two examples of this system, 32 water molecules. This is the number of cores for this machine. And this is the time for free iteration. And show the time for the MPI if you use also only MPI, and here if you use only OpenMP threads. You can see the MPI is more efficient than OpenMP. And this present the speed up about MPI and OpenMP. And also here you can see the speed up is more efficient with the MPI respect the OpenMP. So why using OpenMP? You can say that because the OpenMP involves less communication. And we saw before that the communication maybe can be as a bottleneck for our calculation. So maybe we can use a combination of MPI and OpenMP, and not only MPI or only OpenMP threads. Now show you a scaling an MPI, a combination of MPI and OpenMP. Of course, this nodes has 38 ranks. Our in the Leonardo today our 32. We have 32 ranks. Now here is an example of 190 water molecules. So here we haven't pooled. So now you can see for one nodes all combination MPI per threads, OpenMP threads. So here we have one MPI and 48 OpenMP threads, and here 48 MPI and one OpenMP. So you can see for the limited combination, you can see the biggest difference between all MPI and all OpenMP. But if you can see in this part, we combine some OpenMP threads and the MPI, you can see you you obtain an efficient calculation. Also, if you don't use all MPI. Now, with the two nodes, you can see all the same. No, this is 2 MPI and 48 OpenMP, and this is 96 MPI. And also you can see in this range an advantageous calculation, an efficient calculation. Now for 3 nodes, also here in this region you can see this trend, and also for 6 nodes. If I zoom the 5 nodes, you can see for the 2, 4, and 8 OpenMP, an increase of with respect a totally MPI calculation. This is because you reduce the communication. Now, in this case, we have a crystal with the 30K points grid, so we can use the pools. So you can see in the blue the 3 pools and the red the 5 pools. So you can see also the threads is maintained. So you have to consider a combination of MPI, OpenP threads, and pools to have a drastic reduction of computational time. No, you can see here the same calculation from this point to this is almost half time for the 3 iteration. Okay. So, how to understand how the best way to submit a job to using the CPU resources that you have. Now, if you check, this is the script for the exercise 3. Now, first of all, if you need to know is the size of your node. I showed you before that the booster partition of Leonardo has 32 processor with 4 GPUs. So, but here you can see all information about Leonardo, but every cluster has the documentation that present you how big is the nodes and so on. And now we can start to explore the OpenMP parallelization. Okay, so move to the directory for the exercise 3. Okay. Now, go to the script. Now I put some 3 points to understand to run this script. Now I want to show you how to use 2 OpenMP threads, and then you can run the 2, 4, and 8 OpenMP threads. Now for the 2 OpenMP threads, so we have to understand how many MPI ranks we have. If I want to use 2 OpenMP, remain 16 MPI, because it's 16 times 2, 32 ranks, 32 CPU of Leonardo nodes, no? So number of tasks, number of MPI, I put 16 MPI, and how many CPU per task per ranks? 2. Okay, because this is 2 OpenMP threads, this is 16 MPI. produces the same. Now I have to put how many OpenMP number of threads. I said 2. Okay. Now MPI run. So if you need 4, you have to put here 8 and here 4. Okay. You have to run more than one job now. Not it's not possible with one script. Okay. See, 2. Now respect is the same that before. MPI run, number of MPI. MPI is 16. And then you can modify the name of the output. Now I put here 16 MPI times 2. Okay. Right. And back this script. Then if you wait the output, then modify the script for maybe 4 OpenMP threads. So here put 8, put 4, 8 times 4 is 32. Now modify here OpenMP 4, MP 8, and the name of the output. No, so if you don't modify the name, rewrite the last one. So attention on this. Okay, and then you can see send. You should be able to obtain free, in this case, free output with the 2 OpenMP, 4 OpenMP, and 8 OpenMP. Maybe okay, this is the script. Okay, so you have 15 minutes. Move to the last, but I think the most important exercise for this section is Quantum Espresso on GPU. The Leonardo booster is accelerated with this GPU, so it's good to use it. Okay, in this case, we will use the module that are already compiled in, I hope that works, in Leonardo, and is compiling, uses these libraries, this compiler and the Fortran, the linear algebra, the QBLAS, and the FFT. You can see when you module, you can load the module, the Quantum Espresso module. You can see also the module that are already connected with the Quantum Espresso. Now, Ivan presented you before this morning how the GPU works related with the CPU. So the best way to use the GPU is use 1 MPI per GPUs. So to reduce to the minimum the communication, because the communication now is the real bottleneck, because the GPUs is really fast. So in this case, if we distribute the plane waves along 2 GPUs, so you can use you can see these ranks communicate with GPUs and this with this other. But when you do the MPI sum, for example, this GPU has to communicate with this rank, and these 2 ranks has to communicate to do the MPI sum. Now, if you have more ranks than GPUs, the communication is terrible, because this rank have to communicate with this GPU. This GPU have to recommunicate. This rank have to communicate this GPU and then back, and these 2 ranks communicate each other. So this is a terrible situation. But the best situation is using GPUs with pools, because this rank doesn't communicate only with the GPUs and not with each other. This is the best way to use the GPUs. GPUs with pools, the same number of MPI, the same number of GPUs. So move to the script in the exercise 0 and add this line for the GPUs. So move to the exercise 4. Here you can see two scripts, one for the CPU and one for the GPUs. The CPU is the same that we use, is similar that the example in the previous exercise, and now we focus on the GPU's script. Now go to the blocks. So we add here, I add this line. This is the number of GPUs that we use it. So now try with try a calculation with GPUs. So if you remember, one Leonardo nodes contains 4 GPUs. So now try to use it, all of them. So GPUs equals 4, but also you can try with 2, 1 GPUs. What do you want? So now the number of GPUs is 4. So which is the best value of the MPI ranks that I said before is 4. You can try with 8, but I think you will have a bad time result. So what can we do with the rest of the CPU? We saw in the last exercise, we can use OpenMP. So we have 4 MPI, but the rest of the nodes we can use with the we can use the OpenMP. So 4 MPI, so 8 OpenMP threads. So this is the load module. Sorry, this is the challenge. Answer. Right? How to load the Quantum Espresso module. So you can also do this command on the login node and see which module is used to compile the Quantum Espresso. This is the same. Now the OpenMP threads that we use is 8. Now here the number of MPI is 4. Oh, okay. Because also you can try with different number of OpenMP. Now I put using all the nodes, but also you can try with 4 to OpenMP. And now is the IP define the number of pools. So I said before you that the best way to use the GPU is with the pools. So I can try to put some number. Put 1, 2, 4, 8. I can, maybe a question for you. Can I use 8 in this case?
It would exceed 32, right?
Okay, because we have only 4 GPUs, we can use 8 pools, because the maximum is 1 pool for one GPU. So I have to remove the 8 value. Okay, and this is how to run a Quantum Espresso on GPUs using a GPU. So if you have CPU in a remaining CPU, maybe it's a good idea using the OpenMP. You can try also with 2 GPU. So you need to change the number of tasks, the number of MPI to 2, and maybe using 16 OpenMP. Try it and check the result. Okay. This is the example that I show you now. 4 MPI for 4 GPUs with 8 OpenMP for the GPUs. And also you have the CPU script that is the same of the last 3 exercise. So in this 20 minutes that you have, you can try to compare CPU and GPU and try to understand how many GPUs is necessary to have the same time of the best CPU calculation. So you can try the best combination for the CPU and then try it with GPUs to have the same result, the same time result. And maybe you can, you should be able to create a graph like this with the GPU and CPU times. Okay, I finish the last slide. I want to leave you with this minimal recipe to use it to parallelize Quantum Espresso. This is the good practice. First of all, choose the number of MPI tasks depending on the system dimension. If you want to compute an atoms, that you don't need to use 4 nodes with GPUs and so on. If the GPUs are present, use it. And how use it? 1 GPU per MPI task and combine with OpenMP when possible. This is the best way to use a cluster with GPUs. If there is GPUs, use it, please. The third things is choose the pools. If you can, depending with the number of key points, the number of MPI tasks, and the number of the nodes. Before and set the parallel diagonalization with NDIAG, but only for the very large system with the n bands measured typical here 100. If you have a small system, it is not convenient. And the last things is using how to use the OpenMP threads. So you can see in the previous examples, the advantages is up to 4, maybe sometime in 4 to 8 sometime. But if you use more than 8, you have not had advantages to using OpenMP. this is the minimal recipe if you want to run a PW calculation on a cluster. This is some examples how to Quantum Espresso scaling with the pools, GPUs, but even show before better because here is the bigger examples that are respected with our examples, so you can see effectively the parallelization of Quantum Espresso. But I go on. This is pools API. You can see in the repository that you download today. You can see this slide, so you can see in the when you want. So a special acknowledgement to Ivan Carmineo, Fabrizio Ferrari Ruffino, and Pietro De Lugas to help me with this presentation, and thank you to you for the attention, and see you tomorrow. And maybe I will hear from 2 to 3 p.m. to answer some questions if some people need more help.